Hello, my name is Max. Um, we are going to be presenting about an improved DFA for fast regular expression matching. So other team members are Derek Mayer and Zachary Meyer. So our next slide. So the purpose of the algorithm that we decided to implement is to reduce the amount of memory needed when implementing regular expression matching. This can be seen in the really large DFAs with the paper tested it with 3,000 states and almost 38,000 transitions. So this is where we can see the optimization really take place when scaling the DFA. Also, testing done by the authors found that by applying the delta FA, which in this case, the whole purpose of the paper is to reduce a regular DFA into a delta FA, which is what they came up. It's an arbitrary name that the paper came up with, and a char state compression scheme. The speed of the performance improved over the methods without increasing the space requirements. So basically, this delta FA is a lot faster than the regular DFA.
Okay, and I was just gonna go over the input into our program. Input is a text file that the user specifies. The text file has to be set up a certain way though. The first line, like the 5 here and the one that's shown, is the number of states that the DFA has. So for ours, we're just doing it with 5 states. The next line, the 4, is how many different characters are in the language for the DFA. So this one would have 4, and our program would name them A, B, C, and D. The next number down, the 1, represents the initial state. So for ours, we'd say that state 1 is the initial state. Then the 2, the 5, and the 4 are final states. So for this DFA, we list the final states as those. And then all the remaining lines are the transition table for the DFA. So the first line here, the 2, the 3, the 1, and the 4, means that for state 1, if you get an A, because that's in the first comma spot, it would go to state 2. The 3 would go to, well, state 3 because it's a B, and then the 1 corresponds to a C, or it's in the C spot, so it goes to state 1, and then D goes to state 4. This is our paper, where we got it, and then a link to the PDF, and then Derek was going to go through the implementation of our program, or how it's run.
Alright, this is the start screen of our program. You can specify a DFA file for it to test, so you can have multiple DFAs just sitting around ready to be testing. The one we're going to test is dfa.txt. So right away it loads up the original transition table, and then it shows you the new delta transition table after it runs the algorithm. And from here you can just choose any string you want to test to see the transitions it takes and what final state it ends up in. So if I type in ABC, it'll show that it does each symbol separately, shows you what state it goes to, and then the code that we have, it implements a local table and updates that for every symbol, and it shows that local table there. So after we tried ABC, it says that the last state is state 5, and then it's a final state. If we want to try a different string, I'll just try a longer one. It works, and it'll say whatever I just typed in, the last state is state 2, and that is also a final state.